Okay, so last time we finished with the special adjoint functor theorem. So let me remind you the statement. So theorem, which is the special adjoint functor theorem. So let D be complete well-powered category with cogenerator Q. So then a functor G from D to C has a left adjoint if and only if G is continuous, meaning that it preserves all the limits. By the way, notice, of course, that you can kind of go to the opposite category and formulate the dual theorem with the category which is well-powered, well, in the meaning that we have that all the quotient objects form a set, and then instead of the cogenerator you have a generator, instead of the left adjoint you have right adjoint. So it's just going to the opposite category. And also we saw an example from topology, which is the example of this existence of the left adjoint was the Stone-Check compactification for the functor G, which is just a forgetful functor from the compact Hausdorff spaces to the topological spaces. And another example that I want to consider so it will consist of two parts. So let's call this maybe example 2. And the first part A, is the following. So you consider some functor G from the category of R modules to the category of S modules. So in this case, the categories are of the left R modules and the left S modules. And we assume that this functor, so functor is continuous. So this is the assumption. Okay, since the functor is continuous, well, clearly the category that we consider in this case, the category of R modules, is complete. We discussed this. It is well-powered, which is kind of trivial observation. So the only thing that is not trivial is that any category of R modules exists a cogenerator, but I want to postpone the existence of this cogenerator to the seminar. We need to show, first of all, that the Q modulo Z is a cogenerator in the abelian groups, and then from this we can derive that any category of R modules is a cogenerator. So, but anyway, all the assumptions of the theorem are satisfied, and we can claim so that by special adjoint functor theorem, there is an adjoint functor F, so which is a left adjoint to the G. Now, I can take, say, G of M, right, and I can write this as the Hom over S from S to the G of M. No, just a rather trivial observation. So that's a module over ring S, and for any module over ring S, I have the following identity, right? So the Homs from the ring to the module is just isomorphic to the module. Now, in this Hom, I can use the adjunction and rewrite this as a Hom over R F applied to the ring S, well, and modulo M. Right, so the second isomorphism is just the adjunction. But the conclusion from this kind of special adjoint functor theorem and these two completely trivial observations is that a continuous functor is actually always a Hom functor. So here, of course, I can treat F of S is a bimodule. And the conclusion is that any continuous functor of of course, in this case, when I talk about continuous functors, I mean continuous functors between the module categories, not in more general situation. So any continuous functor is actually isomorphic as a functor to the home functor, which is just the one. So this is a covariant main representable functor. And the bimodual that we use to represent this functor was actually not exactly the home as in the representable functors, because here we use a little bit more structure. So S, of course, naturally is an S bimodule. So when you apply F to this functor, it is naturally a bimodule over S and over R. And hence, when you compute this whole home has an S module structure. Okay, maybe there are some questions about this. Is it clear what I mean about the bimodules? Right. When this is a bimodule, you apply a functor S using one of the module structures, you get an R module structure, but you still have the other S module structure. Hence, this is a bimodule, and this home is not just an abelian group, as it will be in general if this is just a module, but it's actually an S module. Okay, so this is observation A, and there is related observation in part B. So in part B, we consider a dual situation. So let's take functor F to be a functor from the left S modules to the right, R modules. And let's assume that this is co-continuous. So it preserves co-limits. So then, by the dual version of the special adjoint theorem, so say by opposite to the special adjoint functor theorem, we can claim that for this functor F, there is a right adjoint. So there is functor G going in the other direction from R modules to S modules. And of course, which is just a right adjoint. So F is left adjoint to G. Okay. So, but then, since this functor G is the right adjoint and any right adjoint is preserving limits, so G is continuous. Right, so this is right adjoint functors preserve limits. So G is continuous, and now we are in situation of the part A, right? So this G has a very precise structure. We know that the G is isomorphic to the home over R from the F of S to the blank. But we know that if the adjoint functor exists, it's unique. So hence, in this situation, we start with some functor F, which is co-continuous. We explicitly compute its right adjoint. But we know the left adjoint to this home functor. This is tensor product with the bimodule. So the conclusion is that this functor F is isomorphic to the tensor product with the bimodule F of S. So this is over S. Oh. So no, it's not over S, over R. Okay. So the conclusion is that any continuous functor between the module categories is actually a home functor, and every co-continuous functor between module categories is a tensor product with some bimodule. So these two statements, but more oftenly the last statement, is called the Eilenberg-Wost theorem. So the last statement called Eilenberg-Wost theorem. So here we kind of get this statement for free, and there are other proofs of this statement. Well, in homological algebra, we use, for example, 5 lemma. So maybe later when we discuss 5 lemma after midterm, we will consider another proof of this Eilenberg-Wost theorem about the structure of any co-continuous functor between model categories. Okay, and I want to finish kind of with just a statement. So there is the special adjoint functor theorem, and there is also general adjoint functor theorem, GAFT for shortness. And the statement is the following. So now let, as before, D be a complete category. Complete category. G from D to some another category C is a continuous functor. So then G has the left adjoint if and only if for any object C in the category C, well, we can find a set of objects. So I'm going to call this Di. So this is parameterized by some set large I. So this is a set of objects in the category D such that for any object D in the category D and any map F from the category C to the G of D. So we can find an index, little I, in the indexing set I. So this is that of all objects Di. And the map phi from C to the G of Di. And the map F prime, so F bar from Di to the D, such that F is the composition of the G of the F bar and phi. So you can see that we have such kind of long technical condition, which is kind of the like a weaker version of the existence of the initial object. So this is kind of some weak initial family instead of just one object. So I'm not going to prove this. So prove, let's say this is exercise. But you can really solve this exercise, not an easy exercise, but you can use the same logic that we used to prove the special adjoint functor theorem and prove this theorem, well, by proving that there is the corresponding initial object in all the comma categories C, so F, G. So I'm not going to spend some time on this. I just wanted to say that there is a reason why this is called the special adjoint functor theorem, because there's also general adjoint functor theorem. And with this I want to finish this second chapter, which was quite a long chapter, and go to the next chapter, which was chapter 3, abelian categories. And this chapter I want to keep quite short. So I have a hope that I can finish this whole chapter 3 just today. So I'm not going to go into too many details about abelian categories. So first section will be about additive categories, basically the definitions and the basic properties. So additive categories. Okay, so the definition is quite long. Definition. So we start with the notion of AB category. So N AB category. So AB of course stands for the abelian group. So abelian, well, this is not exactly abelian, it's just a very weak version. So sometimes it's also called pre-additive category. So is a category A such that we have two properties. So first, if we look at the home set between any two objects and x and y, then this home set is an abelian group. So this is for any x and y being objects in the category A. So, and condition 2, that the composition map, composition so let's take homes between x and y, and then take homes between y and z, so we can compose them and get a map from the x to the object z. So is bilinear. So here pair f and g is of course mapped to the composition gf. So the composition bilinear map. Right. Notice that this makes sense, right? Since this is a product of two abelian groups, we know what it means to have a bilinear map from two abelian groups to another abelian group. So if you recall the definition of a tensor product by using universal property, you can equivalently say that the composition, let me just for shortness use this just symbol for the composition, and the composition is actually not a map from the product of sets, it's a map from the tensor product of abelian groups, so tensor product over Z. And that's precisely the same thing as the part 2 of this definition, contains exactly the same information. I can say this is bilinear, I can say that the composition is a map from the tensor product. So this is the first part of the definition, and also in this definition I want to introduce the notion of an additive functor. So this is part 2 of the definition. So if A and B are AB categories or pre-additive categories, a functor f from A to B is called additive. So if so the functor is two maps. There is a map on objects and there is also a map on the home sets. So now I consider f as a map on the home sets, and this map on the home sets is supposed to be a map of abelian groups. So if f map of abelian groups. Okay. Let's look at the examples. So, what examples of the AB categories you know? Yeah, so the categories say all the abelian groups, right? So then there is, say, category of the same more or less structure of R modules. And as a special case, you can consider the category of vector spaces over a given field. It will be just a special case of this example. Well, if you know, for example, some sheaf theory, you can consider sheaves, say, of abelian groups or sheaves of R modules, or you can take your ringed space and consider, say, category of coherent sheaves or quasi-coherent sheaves, etc. So this is all examples of such categories. And examples of additive functors, well, you can take, as I've done in the beginning of this lecture, two categories of R modules, and for example, take a home functor and take the tensor product functor. These are additive functors. So say home slash tensor product is something. So R additive functors. So another kind of example you can consider as an additive category, you can take R to be a ring, and in the same way as we we take a monoid or a little bit more restrictive a group, and we can consider this monoid as a category with only one object. You can do exactly the same thing here. You can take a ring and consider this as a category with one object. So let's call this R underlined. So is an AB category with one object. Well, then 3, we can take, for example, all additive functors. Well, there maybe I instead of 3 I introduce some notation. So notation. So if A and B are AB categories, so then there is a notation for all the additive functors. So this thing is the same as func additive from A to B. So you can compare this with the notation where we use rectangular brackets for the all functors from A to B. Now we just use parentheses for the additive functors. Quite standard notation in the literature on category theory. So with this notation, I can ask you a question. So suppose I want to, again, maybe example, suppose I want to understand all the category of all additive functors from the category, so AB category with one object, which is a ring, to say the category of the all abelian groups. So what is this category? Remember, we discussed similar question when we just have categories, not categories with additional structure, and we considered a monoid as a category with one object and consider all the functors from the monoid to the category of sets. So what was the answer? Well, in that case, you have categories, only one object, you have a functor. It's enough to understand where this one object is sent by this functor, right? It will be just some set. And then this functor suppose also preserves the maps. So maps in one category with one object is just the group itself, right? Or monoid more generally. And so what you get by applying the functor is the action of this group on this set. So here, if you do exactly the same thing, this category is one object, so you send this one object to some abelian group, right? And then there is an action of the ring R on this abelian group. So what you actually get is just the R modules. So the category of all additive functors in this case is the same thing as the category of R modules. Okay. So proposition. So we assume that A is an AB category, and we assume that Z is just some object in A. So then the following four conditions are equivalent. So the first condition is that this object Z is initial. The second condition is that Z is terminal object. So third condition is the identity for the object Z is the same as the 0. And finally, 4, if you consider all the maps from Z to itself in the category A, well, this is just a 0 abelian group. Okay? Do you understand the conditions? For example, do you understand what 3 means? Yeah, so on the left-hand side, we have the identity, which we always have, right? This is an element in this abelian group. But since we know this is a abelian group, we have 0 in this abelian group. So this is supposed to be 0 in this abelian group. Of course, we can see more or less trivially, there is nothing really to prove that 3 is equivalent to 4. It's just a restatement. It's just a statement about abelian groups. But this is interesting, right? So in this additional setting of the abelian categories, the initial is the same as terminal, which is maybe quite surprising. But of course, it's not surprising if you think about such examples. So in this case, the 0 module is the same thing as the initial, the same thing as the terminal. So the proof is quite elementary, actually. So if we assume that D is initial, so suppose this initial object, well, then we know that there is a unique map from Z to itself, right? And since there is only, well, we know that all such maps form an abelian group, and there is only one element in this abelian group, hence the identity is the same as 0. So this shows that if the object is initial, then it satisfies, say, 3, and 3 is equivalent to 4. And for the 2 implying 3 or 4, this is just the opposite proof, right? So the same logic, you just, again, use this as terminal object. So we only need to show now that, for example, if identity on the Z is the same thing as the 0 in the abelian group, then we can take any map F, say from the B to the Z. So then you can take this F, write this as the 1 on Z composition with F. You know that 1 is the same as 0. So you take a product of the 0 and F, and this is just a 0 since the composition is bilinear. So as a map from B to Z. Okay, so in first 2 lines I prove that 1 implies 3, and the second 2 lines I prove that 3 implies what? So I take any object and any map to this object, and then I can show that this map is actually a 0 map from the object B to the Z. So hence there is only one map from the B to the Z. So this is a terminal object. Right, so 3 implies 2. Mm-hmm. Well, for example, because this is an abelian, AB category, so the maps from B to Z form an abelian group. In the abelian group, there is at least 0. And if there is something else which is not 0, actually this is 0. Okay, so definition. Again, as before, I assume that I have an AB category, so let A be an AB category, and X and Y are 2 objects in this category. So then we can define a byproduct. So a byproduct of x and y, so is the following thing. So this is an object, and notation for this object is a direct sum, so this is an object in the same category. And also you have 4 maps, so you have this new object by product, and there is a projection to the x, so let's call this P1, and there is a projection P2 to the y, and there is also embedding of the x1 into the byproduct I1, and also embedding I2. So the byproduct is an object, but these 4 maps satisfying several conditions. So such that, so let's say maps P1, P2, I1, and I2 satisfy conditions. And the first condition is that the composition of the P1 and I1 is the same thing as the identity on the object X. So the same for composition P2 and I2. This is identity on the object Y. And finally, the composition I1, P1, I1, P1 plus I2, P2. This is identity on the byproduct. So you can notice, for example, that this direct sum, for example, in the examples of the R modules, this will be exactly the same thing as a product, coproduct, and byproduct. All 3 things will be the same for R modules. But if you want to kind of give these abstract definitions, well, we have a notion of a product, notion of a coproduct, and then you additionally introduce notion of a byproduct in the AB category, which doesn't use any universal properties. It just uses that you have a lot of data satisfying these 3 conditions. So what actually happens is that observation about R modules is true in full generality. So namely, there is the following theorem. So theorem, if as before A is an AB category, we have 2 objects, X and Y are objects in the category A. So then the following are equivalent. So first, X and Y have byproduct, as in the previous definition. 2, there is a product of the X and Y, and as an object, this product is the same as the byproduct with projections P1 and P2. Okay, so if we have a byproduct, well, we can kind of forget part of the data. For example, we can forget in the second statement the embeddings. You just keep the object and keep 2 projections. So I claim that this object with these 2 projections actually is satisfying the universal property for the product. So the product exists, it's the same as an object as a byproduct, and the same projections. And there is an opposite statement, 3. There is a coproduct, and in this case, for the coproduct, we can take the same object as the byproduct with coprojections or canonical embeddings, coprojections I1 and I2. So what I'm saying is that this byproduct contains a lot of information. You can forget part of the information and get a product, and you also can forget part of the information and get the coproduct. And in fact, I claim that the existence of a product and coproduct actually allows you to construct a byproduct, so recover the second half of the data. Okay, so proof. So we show that 1 is equivalent to 2. The proof that 1 is equivalent to 3 is similar. Oh, well, we can even say this completely formally. If you know that 1 is equivalent to 2, then 1 is equivalent to 3 by going to the opposite category. Clearly, the notion of a byproduct is the same as, well, it's invariant under going to the opposite category. Okay, so let's assume that we have 1, and let's derive condition 2. Well, I start with a kind of very trivial observation, but still useful. I want to find the composition explicitly of the P1 and I. So for this computation, I take P1, I plug in the identity in the middle, so I1 P1 plus I2 P2, and I need to keep I2. Right, so I take this composition, and in the middle I plug in the identity, which by that axiom I can write as this sum. And now if I try to compute using distributivity, well, what I can get from this? Well, for example, well, let's look at the first composition. So say P1, I1, P1, I2. So can I simplify this? Yeah, I can simplify this by looking at the first formula, that the composition of the P1 and I1 is just the identity, right? So this composition of the first two maps is just the identity on X. So this is just the composition of the P1 and I2. And the second term, so let's again, let me write this, P1, I2, P2, I2. Now, using the second condition in the byproduct, that the composition of the Phi2 and I2 is the identity, so this will be identity on the Y. So anyway, so the answer, if I continue this computation, the answer will be precisely P1 I2 plus P1 I2. But this is just elements in the abelian group. Right? So by using the cancellation property for the groups, I can conclude that the composition of the Py and I2 is the same thing as the 0. And that's just the general property of the byproduct, right? Just follows from these axioms and that simple computation, that if you kind of take the composition of the projection and embedding with different indices, you get 0. You can believe me, or you can check this, that you can do the same computation, but for the composition P2 and I1, and you'll still get 0. Okay, it's just a simple observation. Now, let's take the data. So we have byproduct, from which we keep two projections, P1 and P2, and suppose I have some other object T, and the map T1 to the X. There is a map T2 to the Y. So I'm trying to show that the universal property is holding for the byproduct of the X and Y, right? So it means that I need to construct a unique map. So let's call this map H. So somehow I need to show that there is a unique map H such that two triangles are commutative, right? If I can do this, that's exactly the proof that 1 implies 2. So I just, well, first of all, I can define this H. So take as an H just the sum. So I1 T1 plus I2 T2. So let's take H to be this thing, just by definition. And first of all, if I take projection, just for shortness, let me write instead of two formulas, P1, comma 2, composition with H. It means that I consider two cases, composition of P1 and H and P2 of H. So what if I do this? Well, for example, let's say I take P1, I kind of add this P1, so this composition of P1 with I1 is identity, so it will be just T1, but the composition of the P1 with I2, as we just showed, will be 0. So what's left in this formula is just T1, right? But now then I can do this for the P2, and then I'll get T2 by the same computation. So this is T1 or 2 with the same index, right? But this precisely shows that this map H makes both triangles commutative. So this is nice. So now we only need to show that this map is unique, right? So to show uniqueness, we need to assume that there is another map H prime from T to the byproduct such that it satisfies the same condition. So P1 or 2 composition with H is T1 or 2. So we need to show that in this case H prime is the same thing as the map H. Okay, so H prime, this is a simple computation. I take a composition with the identity on the byproduct of x and y, and I know that by the third property this is just that sum. So I1 P1 plus I2 P2 H prime. Now I can open parentheses and I know the compositions of the P1 and H prime, so this is just T1, so what I'll get is precisely I1 T1 plus I2 T2, which is by definition H. So that's all. Now we know that 1 implies 2, right? We show that there is a map and this map is unique. Now let's go in the other direction and show that 2 implies 1. Okay, so now I have a product, and first of all I want to construct this canonical coprojections I1 and I2. Well, I use the universal property. So for example, let's take product of x and y. There are projections P1 and P2. And let's take object x, and the map to the x will be just, of course, the identity on x, and for the map on the y, I'll take 0. Well, you know that we can do this. This is AB category. Between any two objects, there is a 0 map, so I can take it. And there is a unique map here, which is exactly I1, right? Since you know that you can go like this, I1 and P1, and this will be the identity. And also from this definition of I1, you can notice that the other composition with I1 and P2 is 0, which we earlier derived from the definition of the byproduct. So that's an I1. And yeah, so maybe I write this as a formula. P1 I1 is identity on the x. And you can use the same logic and show that, oh, just switch. Instead of x, you take y. Here you get 0. Here you get the identity. So I just want to write. Similarly, there is map I2 from y to the product of the x and y, such that the composition of the P2 and I2 is the identity on y. Okay, so what's left is to check that this condition here from the definition, the last one, is satisfied. And for this, I just again draw this diagram with the product of x and y. And now I take object, the same object x and y. And so these are projections P1, projection P2. So there is a the same maps, P1 to P2, so that here there is a unique map. Well, for example, the identity map clearly works in this situation. But you can also do the computation and say that the composition of the projection P1 or P2 with the I1 P1 plus I2 P2, right? So this composition is just another map here. I take these compositions with the projections, and what I'll get is that this is, again, P1 and P2. Well, it's more or less the same computation as we've done several times already. You just compute this. Now, for this sum, we can see that this is another map making these two triangles commutative. Hence, since this map is unique, right, the identity map is the same as this one by the uniqueness of the map for the product. And this finishes the proof of this proposition or theorem. Okay, so there are two simple remarks. So first, that you can generalize this to the several objects. So say if you have x1 up to xn objects in some AB category, well then you can define a notion of the byproduct of all these objects. Well, I know, just shouldn't be called byproduct because there are more than two objects, or some generalization. And in this case, you have projections and embeddings for any I, and you'll get the same conditions that the pk ij is the delta kj, and the sum of the ik pk is the identity on the product of all these objects. Just generalize this by induction. And the second remark is that if you have a map F from one such sum to another such sum, so these are finite sums for simplicity, so between 1 and n, and this is for j between 1 and m. So then you can introduce the matrix of F. So F kj, this is composition of the projection map F and the embedding with the index j. And you can notice that the compositions correspond to product of matrices. That matrices that we associated with the map F and given decomposition into sums of the source and the target. So it's kind of standard linear algebra, but now done more generally in any AB category. Okay. So definition. An additive category is an AB category with 0 objects and byproducts. So this means that I assume that I take an AB category, I assume that there is a zero object, which is the same thing as initial object or terminal object, as we just saw. I assume the existence of such object, and I also assume the existence of a byproducts for any two objects x and y. Okay, so that's the definition. This is why we need the notion of the byproduct. Well, we can see this is more or less the same thing as the product or coproduct in the category. And the existence of these products or coproducts is part of the definition of additive category. So now I want to finish this section with a couple of easy propositions about relation between all those things. So let me say that if A is additive category, suppose we have two elements, f and f prime, in the home abelian group from x to y. So then the addition, so f plus the f prime, so this is the so this home set is an abelian group, so there is a binary operation that gives this set a structure of an abelian group. So this addition I can recover, well, for example, using the codiagonal coproduct of the f and f prime, and then finally composition with the diagonal. So the codiagonal is for y, and the diagonal is for x. So I'm writing here the coproduct of two maps, but I cannot just as well write the product here or write the byproduct. This still will be a correct formula since all these things are the same. Okay, proof. Now if you just recall the definition of the diagonal, so then just from the definition you can see that the composition space projections for the diagonal map is precisely identities on x. And the same will be true for the codiagonal, right? So if you write the codiagonal, so then the recomposition of the codiagonal with the canonical embeddings still give you the identity for the object y. Okay, so now let's try to compute the right hand side. So you can take the codiagonal on y, coproduct of two maps, and then additionally I plug in the identity map. So I1 P1 plus I2 P2 composition with the diagonal. So we can open this. So the codiagonal coproduct of the f and f prime. Now using the formula that we just derived, I can simplify this and write just I1 plus the codiagonal on y, f coproduct with the f prime, composition with I2. Now, since this is a coproduct, I know how to compute the composition of the coproduct and the canonical injections. So I can rewrite this as the codiagonal. Now this will be just I1 f plus codiagonal I2 f prime. And finally, using the second result, I can just write this as an f plus f prime. So this is the end of the computation. So in other words, this proposition is saying that putting this structure of an abelian group on the home sets is not necessarily actually, you can derive this structure from this composition. So it means that potentially you can come up with another axiomatics for the additive category. Well, that just follows from the definition, how you define the diagonal map. You take a product of the x with itself, right? You have two projections, and now the maps that you use is just the identity here and here, and then by the universal property you have the diagonal. But this exactly means that if you apply the diagonal, then you apply the projection, that's you get the identity. Here? Mm-hmm. Нет, оно же все одно и то же. Я же только что доказал теорему, что все три понятия совпадают.
Да, у нас одни в x с x, вторые в y с y. У нас пешки, они из x в x, а ишки из y в y.
Yeah, that's true. But я думаю, что это все равно не проблема. Все, что нужно сделать, достаточно просто убедиться, что это по-прежнему тождественное отображение. Давайте посмотрим. Ну, сейчас давайте посмотрим. Сейчас у нас здесь вот это будет отображение из x сюда. Да. После этого, ну, например, возьмем P2. Это будет отображение, ну, не знаю, здесь можно написать что-нибудь типа x, y вместе, да? Соответственно, здесь будет кодиагональ. Так. Ну, а здесь у нас будет такое отображение, значит. А это как раз есть вот это самое отображение. То есть мы что делаем? У нас есть, ну, у нас здесь есть, как бы это нарисовать красиво. Есть, например, x, да, у него есть проекция P1. А здесь, соответственно, есть еще отображение в y и есть вложение y1, да? И есть то же самое для второго с f' с i2. Вот. Ну, то есть на самом деле то, что используется, это как бы вот эта диаграмма. Тогда непонятно, как это написать. Ну, это правда, да, непонятно. Но на самом деле берем их вот так, как нарисовано на этой диаграмме. То есть, на самом деле, ну, наверное, да, давайте, если хотите, я вот вместо вот этой строчки, so I need to take out this line and replace this by this diagram, where we can see all the maps. And then I just do the same computation more or less, right? I know these two compositions, and I know that when I take compositions with the map F with the, say, I1 with the co-product of these maps. I take composition with I1, I get exactly I. Take composition with I2, I get exactly F prime. So really the computation works, but I agree. The formula that I wrote here doesn't make sense exactly. Okay, anyway, so I think we understand the proof of this proposition. And from this I want to derive another proposition about the functors. So now suppose we have two additive categories. So if A and B are additive categories, so then the functor f from A to B is additive if and only if F maps byproducts to byproducts. Again, as before, instead of talking byproducts, I can talk about the binary products or binary coproducts. It still will be the same condition. And now using the previous proposition, in this case, I want to say that this is completely trivial statement, right? In one direction, if you know that the functor is additive, then clearly it maps byproducts to the byproducts, right? So since byproducts is just defined in terms of the existence of the maps, and there is a relation that the sum of two maps is the same as the identity, any functor maps identity to the identity, so the maps that you're supposed to use for the image byproduct is just a functor f applied to the I1, I2, P1, and P2. So there are no surprises here. And in the other direction is also more or less trivial, right? So you know that in this case byproducts are mapped to the byproducts, and you know that you can recover the additive structure by looking at those compositions. So it's just a simple observation that for the sum of the F and F prime, so this is mapped to the, so for the byproduct of two maps, this is mapped to the byproduct of two maps, and also functor f is preserving the diagonal and codiagonal. So it preserves everything that we need, for example, to recover the additive structure. So if the second condition is satisfied, also by the previous proposition, the first condition is satisfied. Okay, so let's go to the next section, where I want to define the notion of the abelian category. So first of all, before I give a definition, we can notice the following. If we have two objects and a map between those objects, so let's assume this is an additive category. So